To another monthly. Oops. Okay, welcome to another monthly Energy Transition Group meeting, and I'm Doug Beckett, facilitator of both the Prince George Electric Vehicle Association, which is a co-partner in hosting these monthly events. And we're going next month, we're going to have one of the salesmen at a dealership, new car dealership in Prince George, coming to talk to us. Denham Morrison. He's with Wood Wheaton. And I did a circuit of all the dealerships a couple of days ago. And Wood Wheaton had the most variety of makes and models on hand. And they had this one salesman who blew me out of the water with his knowledge of electric vehicles. By far the most impressive I've come across in years in Prince George. So I asked if he would come next month to discuss his insights. I know the Energy Transition Group's not supposed to be talking about electric vehicles because they're here, they're happening. But just with the current tariff environment, the tariffs on Chinese electric vehicles, the leadership China's doing, I thought it'd be good to take a look at what various North American automobile manufacturers are actually doing with electric vehicles. That's very impressive. So please keep that in mind for next month. I'll advertise it a little bit. We'll try to get a larger turnout. And then with that, please let me know if anybody would like a presentation by a fairly new EV owner about what it's like to start driving an electric vehicle in recent times. A very knowledgeable individual. So they've offered to do so, but only if there's interest expressed. So let me know. And then this month, we have a professor from the university here, Dr. Steve Helle, and we will be definitely on the energy transition topic about sustainability of energy and energy efficiency. And we even have props. So we'll try to set up the camera once in a while for the online people to be able to see the props. So are we allowed to interrupt you during the presentation with questions, answers, and discussion, or do you want it held to the end? You're open, so we can make it a discussion. So feel free to interject with questions, clarification, and so on as we're going through. Thank you very much.
Thank you. All right. So what I would like to talk about today, figure this out. Yeah. Okay. Yeah. So sustainable energy. I want to talk about more than just climate change, all the other impacts that energy has. I'm going to talk a bit about how I look at the energy system, and I don't know, I'm hoping that it's a nice framework for people to have to look at how we can maybe improve our energy systems. And I'm going to go through two examples of a life cycle assessment. A gasoline car versus an EV, and a natural gas furnace heating versus an electric heat pump heating a house. So two common electrification examples. And then I'm going to argue that it's not enough. For the record, I have an EV, and I also heat my house with a heat pump, and I also have a heat pump that I travel around with all the time in case I get too hot or too. Okay. So sustainability. Actually, I teach a course on sustainability, and every year I ask the students for the definition of sustainability, and nobody can come up with one, and I can't come up with one. I've taught the course twice now, and I still don't really have a definition for what that word means. You know, meeting the needs of the present without compromising ecological integrity or the needs of future generations, that is Engineers and Geoscientists BC's definition. And it's a balance of environmental protection, social well-being, and economic prosperity. And how you weigh those is up to you. So you could weight them equally. You can say economic prosperity is more important than the environment. You can say the environment's more important than anything else, because without a functioning environment, we can't have a functioning society. So lots of room for interpretation. But what I'm going to be mainly talking about is environmental sustainability, and with a little bit of social aspects. Energy transitions. That's the name of this group, energy transitions. This is global energy consumption from our world in data. And we go from, so back before 1850, wood-based energy, then starting in 1850, started using coal, predominantly coal-based energies up until about 1950, and then came the era of oil and gas, which I would say is going on right now. Energy transitions in the past, if you look at the wood line, the biomass at the bottom here, when we transitioned to coal, we kept using biomass. We started to even use more of it. When we transitioned from coal to oil and natural gas, we use more coal. So we switched what we were using coal for, right? We were using it to power our boats and our trains. That was replaced with oil and gas, but we used coal still for industry, and there was more demand for cement and steel, and so on. And so the next major energy transition will be from oil and gas to something else. Yeah, so coming back here, there's a number of concerns with this. One is our resource availability. So how much oil and natural gas do we actually have? Do we have enough? Another is climate change, burning them, greenhouse gas emissions, changing the climate, acidifying the oceans. Whenever you burn anything, air pollution, and all of this is affecting biodiversity. So these are some of the major concerns. Greenhouse gas emissions over time. Going back to 1850, I've divided the greenhouse gas emissions into 4 equal chunks. What's important with respect to climate change is the total amount of CO2 that we emit. So it puts CO2 in the atmosphere. It basically, a fraction of it will stay there for thousands of years, and the temperature change is directly proportional to how much CO2 we put in the atmosphere. The CO2 we put in the atmosphere is the area under this curve. So we're putting more and more in all the time. And we have targets to stay below 2 degrees Celsius. Our greenhouse gas emissions need to do that. So they need to be 0 by just shortly after 2070. This is assuming we don't have negative greenhouse gas removal technology at large scale. We want to stay below 1.7 degrees. We need to have 0 greenhouse gas emissions by 2050. And if we want to stay below 1.5 degrees Celsius, we basically need 0 greenhouse gas emissions pretty much now. The global target is well below 2 degrees, aiming for 1.5. So we're kind of getting into that range. So we need to make, if we want to reach these targets, we need to make major changes as quickly as possible. One other concern with sustainability is inequality. This is a chart from the United Nations emission gap report from a few years ago. The top richest 1% of people on the planet emit 15% of global greenhouse gas emissions. The bottom 50% of the poorest people on the planet emit 7% of greenhouse gas emissions. Yes.
global. Sorry, I was just curious how you divvy up the industrial emissions into that when we talk about it on almost on a per capita based on its
Yeah,
income.
so that is an excellent question. So it's not my analysis.
Okay.
But my understanding is it's primarily based off of wealth and purchasing what you buy. So the rich people buy a lot of stuff, so the industrial emissions get associated to the stuff they buy.
So I wonder if they would take all the industrial emissions in Canada and then equally divide it amongst all the people and then rate it.
So it's a little bit more complicated than that, but yeah, so is based on also on global trade. So we're fairly greenhouse gas intensive here, our industry, but we export a lot.
Okay.
So those greenhouse gas emissions associated with our industry, some of those get exported to the people buying our stuff. And then they look at the wealth distribution in the countries that are buying everything and sort of try to proportion greenhouse gas emissions. That's my understanding. But again, this is not my analysis. But they do try to account for all of that and try to basically assign the industry emissions to the person who's using the product.
Okay, that makes sense.
Yeah. And so basically the bottom 50% of the people, wealth-wise on the planet, do not purchase much. So this is an issue, an equity issue, a fairness issue, so social sustainability issue. And I'm not sure if you are familiar with the planetary boundaries concepts. Anyone heard of planetary boundaries? So this is a study, it's been around, I'm going to say, for a decade or so. They keep updating it. It's out of the Potsdam Institute, I believe, in Europe. And they're looking at planetary systems as a whole. So one is the climate system. So as we put greenhouse gas emissions into the atmosphere, we're changing the climate system, right? We're changing weather patterns, circulation, we're changing where the droughts are and floods and fires and all of that. And so they sort of say that after a certain threshold, we'll trigger a lot of sea level rise and changes in ocean circulation patterns, like the AMOC circulation in the Atlantic might slow down. There's all these potential for tipping points in the climate system if we put too much greenhouse gases in the atmosphere. So they sort of say there's a planetary boundary. And I think they put that at about somewhere between 1.5 and 2 degrees Celsius, so which is what our target is. But they're also looking at other systems. So the climate system is this one here. This is toxic chemicals. So they're worried about just putting out a lot of toxic chemicals. So you can go to any place on the planet, the deepest trench in the Pacific, the top of Mount Everest, and you'll find microplastics. You could take a sample from any person, any part of their body, and you will find microplastics. You'll find pesticides in us. You'll find various endocrine disrupting chemicals, PFAS, all kinds of stuff. And there's concerns, there's some indication that all of these chemicals are not good for us. So there's concerns over that. So they put a planetary boundary on that and sort of said that we're past that. We should stop putting toxic chemicals in our environment that are persistent. This one here is biodiversity. So there's elevated extinction rates going on right now. This could potentially lead to ecosystem collapse. So we should try to protect biodiversity. The one down here is nitrogen and phosphorus. So we're putting a lot of fertilizer out in the environment, and that's affecting ecosystem functioning. And again, there's potential tipping points where if we put too much out there, that'll change the whole functioning and types of ecosystems we have. And change usually is not good for us. We're used to what we have, and change is always disruptive. These other ones, this one is land use, this one is water use, and the ones in green we're still good on. This is ozone depletion. So we did have an ozone layer problem, mainly solved that one. This one is aerosol loading, so air pollution in the atmosphere. And the last one is ocean acidification, which is not yet a large concern, but it will be with continued greenhouse gas emissions. So this is planetary boundary framework. And the idea is there's these potential points in our global systems that if we push past those points, there could be irreversible changes that we don't. Okay. So those are some of the major high-level sustainability concerns, right? And so there's a few of them. This, and I'm sorry about the small font, this is my sketch of our energy system. So this is how I look at how we use energy. On the left here is primary energy. So this is the stuff we harvest from the environment. So it's the fossil fuels we dig up, coal, oil, natural gas. It's the trees we cut down. It's wind, solar, geothermal, hydro, all the stuff we back from the environment. The next one over is secondary energy. This is the fuels we buy. So you go to the store or the gas station, you buy gasoline, buy propane, buy natural gas. These are the fuels up here. And the electricity we buy and heat. Useful energy, we convert all these energy sources into either work, motion, so we're moving things, or into heating and cooling. So we're heating something up or we're cooling something down. Over here, which I'll talk about a bit later, is passive systems. So this is the design of the car, excluding the engine. So how heavy it is, how aerodynamic it is, rolling resistance of tires. The design of our buildings, excluding the heating and cooling system. So it's how much insulation there are, how many windows you have, whether you have solar aspects or not. So it's a passive system because it's not mechanical. So it just sits there. But it's what we use energy. It's a system we use the energy in. And this is the last column is the service provided. So that's, we want to go from point A to point B. We want to keep our house nice temperature. We want to keep our food cold. We want to have hot water for washing and so on. In our current system, we mainly use fuels here, and we mainly put them through heat engines to make work, or we burn them directly for heat. So that's our majority of our energy. From a thermodynamic perspective, that's bad. Both are very inefficient. So turning a fuel like gasoline or natural gas or coal into work is very inefficient. Second law of thermodynamics limits the efficiency you can get there. Not a good way of doing work. It does convert into heat, but again, it's not ideal. What we want to do is use work to do work. So we want to use electricity that we harness from work, so like sunlight or wind or hydro, that's already in the form of work, can be converted to electricity with close to 100% efficiency. And then electricity can be converted into work with close to 100% efficiency. So it's way more efficient. And we can use electricity for heating if we need to, because we can use heat pumps, which have a very high 300% or so efficiency. So ideally, we want to electrify as much as possible. And I'm going to run through two examples here from a life cycle assessment point of view. So car, internal combustion engine versus an EV and a heating a house, natural gas furnace to a heat pump. So I have a box. This box represents energy consumption. So the volume of the box is how much energy we're using. And I made a box because I wanted to divide sort of the efficiency into three different components. So the bottom one is the efficiency of the heater here, or the efficiency of a motor or an engine in a car. The side one is sufficiency, So that's how much area you have to heat if you live in a big house or a small house. Or for a car, it's, you know, how far you drive. Driving a few kilometers a day, or you're driving hundreds of kilometers a day. And the vertical axis is the efficiency of the passive system. So in the car, it's how aerodynamic the car is, or how heavy the car is. In the house, it's how well insulated the house is. So these boxes, the one on the left represents the energy used for heating an average size house with average insulation with a natural gas furnace. The one on the right represents the energy used to drive a typical car 15,000 kilometers in a year. We can electrify these, and the box gets smaller because electricity is way more efficient. So heat pump will use 1/3 the energy of a natural gas furnace. So my box is now 1/3 the size. An EV, they tend to be actually more aerodynamic, better rolling resistance on the tires because they try to maximize the efficiency because the batteries have less energy than fuel tank. So there's a little bit of savings on the passive energy, and an electric motor is way more efficient than an internal combustion engine. So we get a much smaller box. So our energy consumption has gone down quite a lot. Costs for energy for the EV, it's also gone down. The energy cost for the electricity for the electric vehicle is probably somewhere around 1/10 of what you would pay for gasoline to drive the same distance. For the heat pump, unfortunately, it's about the same. So the energy cost of electricity to provide heat for a house is about the same as buying natural gas for the same heating. So I'm going to look at these two examples through a life cycle assessment. So life cycle assessments, they can be very involved, and they're very big and lots of data, lots of number crunching. It's basically a whole lot of accounting. So what we do is we look at everything. So here we're using a car, we're heating a house. So we can look at how much gasoline you're using and what's coming out of the tailpipe of the car. We also are going to look at the rubber coming off the tires and the brake pad wear. So all of the, and even the road that you're driving on, wear of the road. The house, looking at, you know, the operation of the furnace or the heat pump, including refrigerant leaks from the heat pump. But we also look at fuel production. So making the gasoline, making the electricity and all the impacts, everything that goes into that, all the materials, moving it around. We look at what happens at the end of the life of our equipment. We look at making the car, making the heat pump, mining the materials to do that. So these are very involved exercises and basically a lot of accounting, a lot of materials. So the first step is you just do a huge inventory of everything that goes into this diagram and everything that comes out. So all the resource inputs and all the waste to the air, to the water, to the soil. And you'll have like 10,000 different chemicals going in and out. So then the second thing you do is you have to sort of aggregate those into common numbers. So you take all the greenhouse gases that are coming out of the system and you put them all in the same units and you add them together. And then the third thing you do is you look at all these different impacts, and I'll talk a bit about the impacts on, I think, on the next slide. And you try and say, okay, well, put them into, the method I'm using today puts them into 3 categories. Ones that affect your health, ones that affect the ecosystem functioning, and one that affects resource use. So you get basically 3 results out of looking at this. This is just an example. This is some of the inputs that go into an EV. So there's a whole bunch of energy that goes into manufacturing an electric vehicle. Almost 10 tons of coal is used in making an electric vehicle, according to the EcoInvent database I was using, which is the standard life cycle assessment database. So I'm using the most common data out there. And you know, there's gold and tellurium and copper and silver and these other rare metals. So those are just a very small fraction of the inputs. This is a very small fraction of the outputs. And the one I chose because it was the smallest list to show is just the chemicals that come off of tire wear, brake wear while you're using an EV. So there's all kinds of things here, a lot of metals, some organic carbon, some particulate matter, some sulfur dioxide, apparently. So, and these chemicals have different impacts. So sulfur dioxide is an acid gas. It could lead to acid rain. So that one will go into a category of chemicals that cause acid rain. Particulate matter, that's a health concern. We breathe that in, that's bad. So that goes into particulate matter category. The metals are potentially toxic. They could be carcinogens, so they go into carcinogen category. These are the various categories. So climate change, greenhouse gases, toxicity, radiation, particulate matter formation, smog, air pollution, acid gases, as acid rain, toxic chemicals, fertilizers that can cause algae blooms, ozone depleting chemicals, and all the resources, so all the metals and fossil fuels and water and land. So all of these things get added up, grouped and added up. Here's some results. This is just the greenhouse gas emissions. And here we have greenhouse gas emissions from, this is from making and using the gasoline to drive a gasoline car. And this is from making and using electricity to drive an electric vehicle, making and using the natural gas to run a furnace, and making and using electricity to run a heat pump. So electrifying, massive decrease in greenhouse gas emissions. So excellent, right? This is if now we include the greenhouse gas emissions from making the car, which is this, and from making the heat pump. So you have an increase in greenhouse gas emissions. And just want to come back here. This is the greenhouse gas emissions from making the electricity to run the heat pump and electric vehicle. Quite small, so it really depends where the electricity comes from. So in BC, our electricity comes from hydro. So this is a graph that compares greenhouse gas emissions from a whole bunch of different sources of electricity. And hydro is right here, it's the smallest. So we have a relatively clean grid. The ones on the left that are really big are burning fossil fuels to make electricity. So they release a lot of greenhouse gas emissions. And then we have nuclear, wood, hydro, solar power, wind, geothermal, and this is the BC grid, the last one, which is a lot higher than hydro. So the reason the BC grid is a lot higher than hydro is because we actually import a lot of electricity. And like I said, I have an electric car, I have a heat pump. I'm interested in my carbon footprint. I've always been interested in what is the greenhouse gas emissions associated with BC electricity. And it's been hard to find numbers, but I have found a few numbers. So the one on the left says it's almost 100 grams of CO2 per kilowatt hour. That's from the EcoInvent database, my life cycle assessment database. And this is broken down into the sources here, and the yellow is all the emissions from imported electricity from Alberta and the States. So because we're importing fossil fuel-based electricity from outside, that adds to our footprint. There's a website called Electricity Maps that shows real-time data on what we're importing electricity and gives hourly carbon footprint, which a few hours ago was 84 grams of CO2 per kilowatt hour. That's this black one here. And these are other sources. This is the official number for BC. It says 10 grams, so an order of magnitude less than the EcoInvent database. And this is one from Environment Canada that includes emissions from reservoirs, the methane bubbling out of reservoirs. So the greenhouse gas emissions from electricity in BC is anywhere from 10 grams of CO2 per kilowatt hour to 100 grams of CO2 per kilowatt hour. So it's an order of magnitude to play with. But I've been using the EcoInvent database. Yeah, so back to life cycle assessment. These are all the different categories of impacts. So there's the carbon footprint, which we care about because of climate change, but there's, you know, particulate matter, ozone formation, and all of those other things. So there's like 20 of them. And it's kind of overwhelming because you get numbers for all of these various impacts. So what the life cycle assessment does is it says, okay, well, particulate matter, that causes respiratory disease, which affects our health. Ozone formation causes respiratory disease, which affects our health. Climate change, global warming causes increases in disease, which affects our health. It affects our food, which affects our health. It damages fresh water and terrestrial species, so it damages ecosystems. So it basically groups everything into damage to human health, damage to ecosystems, and damage to resources. So I can go back to my two examples. Now, I can't. Oh. And look at this. So this is the life cycle assessment results for ecosystem quality. So the effects on ecosystems of electric vehicle, which is shorter bar here, versus a gasoline car. And this is the effect on human health of electric vehicle versus a gasoline car. So where there was a huge difference in just looking at greenhouse gases, when we look at these other impacts, they're smaller. And it's interesting. So this is for, I did 15,000 kilometers of driving, so about 1 year of driving for the impacts. And so for human health, the units are in disability adjusted life years. And the numbers are fairly small, but basically saying that 74 gasoline powered cars driving around for 1 year is equal to 1 disability adjusted life year lost. So someone's either dying a year early or someone's sick enough that they're basically incapacitated or ill health for a year from 74 gasoline cars driving around. Wait, I think actually 64 gasoline cars driving around or for 74 electric vehicles driving around. So the electric vehicles have a slightly smaller impact, but still fairly significant. For ecosystem quality, the axis is in extinctions per year. And basically it's 1 extinction per 66,000 electric vehicles driving around, which you might see in Prince George for a year, or 1 extinction for 42,000 EV. Sorry, 66. Yeah, 42,000 gasoline cars or 66,000 electric vehicles. And here's the same thing for space heating. Heat pump versus natural gas furnace. So heat pump is better, but the impacts are still quite high. So from a greenhouse gas point of view, heat pump and EV are great, but when we look at all of the other impacts on ecosystems and health, they're still better, but it's not enough. So coming back to my energy diagram, we need to do electrification, which is here in the middle. So we need to electrify our heating and cooling and our cars and all the work that we do. That electricity needs to come from low carbon sources like it does in BC, but we also need efficient passive systems. And I think I'm going to argue also sufficiency. So passive system, well-insulated house, insulated hot water tanks, so you're not losing heat recovery on your drains of your hot water, daylighting, so you use less lights, lightweight and aerodynamic vehicles, so they use a lot less energy to travel. Sufficiency is doing with less, but still enough for a good quality of life. This is a study from Cullen and Allwood. And they looked at the design of passive systems and how much energy we could save. And I highlighted the two that I'm looking at, heating houses and cars. And they basically say with properly designed buildings with insulation and taking use of solar gain and not too many windows, a house will use 98% less energy than a typical house. So now instead of a furnace that has to or a heat pump using 100 units of energy, you only need 2 units of energy. And for a car, using current technology, using lightweight materials, same size car, like not a big pickup or big SUV, but a car that could hold 4 people and go from point A to point B. But lightweight, low rolling resistance tires and aerodynamic, 90% less energy to move around. And another massively important passive system is how we design our communities. So do you have to travel 20 kilometers or 30 kilometers to go from point A to point B, or can you just walk out the door and walk to the store and don't have to get into a car? This is a graph of energy use per person traveling in a year on the y-axis versus population density of a city on the x-axis. So here we have Atlanta in the States, massive energy consumption, very low population density, urban sprawl. And here we have Barcelona. This is what they look like. So this is Atlanta, Barcelona, same population. Barcelona uses an order of magnitude less energy for people moving around. Plus, this is all a problem with cars that EVs don't solve. So car crashes, sedentary travel, noise, EVs solve noise, but all kinds of problems. Sufficiency, I think I'm running out of time, is living within our means. So this is around equity and energy use justice. So everyone has access to a place to live and food and water and clothing, but not too much. So this starts, I know this is radical, but it addresses the inequality issue. And yeah, so this is, so just I don't think most people will like this, but I'm just gonna, as a thought experiment. So if you live with what's here, so which could give a decent living standard if it's in a nice community, you would need about 15 gigajoules of energy a year to provide everything that was there. So for comparison, in Canada, we use about 350 gigajoules a year. So this is 15 gigajoules down here, this little box, and this is what we use in Canada. So this is what you need for a good life, the minimum, and this is what we use. So whether we go all the way, to what was on the previous slide or not, there's still room for improvement. So I'll end with this. This was my example. If we go to a well-insulated and smaller house and an electric bike instead of electric car, we vastly reduce our energy consumption. So we're now being sufficient. We have optimized our passive systems. We still have electrification. And from a life cycle assessment perspective, these are all the life cycle impacts sort of stacked one on top of each other. Here we have, gasoline car, electric car. This assessment method actually put the electric car as being worse than the gasoline car, and e-bike. Natural gas furnace, heat pump, both in a regular house, heat pump in a very efficient and small house. So the impact is orders of magnitude less. And so we need to reduce greenhouse gas emissions to zero as fast as possible. But we also need to be concerned about all the other impacts of our energy use. Electrification is good, and does reduce our energy demand by about a factor of 3, but it increases our material demands and increases all the other impacts. So we really need to optimize our passive systems, and you can optimize the passive, like insulated house, it doesn't change your quality of life. Triple glazed windows or a few less windows, slightly denser communities, aerodynamic car, relatively minor impacts with much less energy consumption. We can reduce our energy consumption by an order of magnitude with passive systems. And we could reduce our energy consumption by another order of magnitude if we voluntarily live a simpler life. Yeah, so that's my argument. A little bit radical at the end there, but I think if we truly want to solve our reducing our greenhouse gas emissions as quickly as possible, we need to do major things. And if we do major things and we live a simpler life, so times are a little bit crazy now, right? Simpler life is cheap. It's more resilient, stronger community-based. It might help with things other than just energy and climate. Pardon? How do you start?
Yeah.
Yeah. So that's a that's a question for you guys.
Well, yeah, you could do several things like instead of building a coal plant, let's build nuclear, because that's the best way to do it.
Yes.
Instead of designing a city like the Irving cities down in the States, you make like a condensed mini Irving and mass transit everywhere. So that means changing government, changing education is the key component there, but we don't have enough time.
Well, yeah, so I think your points are excellent. I think a good place to start is electrification. I mean, we need to do that no matter what. I think community design, you need to stop the sprawl and more infill. And even like, I bike around town as much as possible, but as a biker, if I had to describe Prince George with one word, I would say hostile. And I never recommend to anyone to bike here. It's horrible. But there are places like you can put in bike lanes, right?
Yes.
Protected bike lanes, and it's not expensive. So that's
I know, but you got the hostility. They've done it in even in Edmonton. They put bike lanes in Edmonton, and they've tore them all out because they don't have people buying into it. Yeah,
but there are places. There are places
where it does work.
Where it does work, and it does tend to be places on the high population density. So here in this region here, the sweet spot, a lot of biking. Here you really high population density, you get a lot of walking. And here you actually have cities, not all of them, but a lot of them actually have a lot of biking.
Like motorcycles and stuff like that.
It should be electric.
And it should be electric. But also there's no lights. They don't have traffic lights, and traffic flows much better than any North American city. I'm sure there's a lot more deaths. But
I think North America is how you don't build a city.
Yes.
Right.
Oh, I agree. North American ideals are worse.
About 1987, I was in Sweden, in Stockholm at the time. You went to intersections and there were traffic lights for the cyclists, traffic lights for the walkers, traffic lights for the cars. It was very oriented to cycling and walking at the detriment of driving. And I think it's Sweden that also prioritizes the clearing of routes in the interests of females. And that primarily then means sidewalks and going to hospitals, places that females work. And it's made a massive improvement to the whole transportation in Sweden. So there are different ways of doing things. It's interesting.
I think you need it. I think our city should provide choice. Like right now, if you want to move around in Prince George, you don't really have a choice.
Yeah.
You need, yeah, a car or don't go.
Or again, mass transit.
Which is
you can't
not,
have a
which is
car.
not great here.
I know, and you take a look at London, the center of London does not allow certain cars. You have to have a special permit and stuff like that. And yeah, Canada's, we just, we're too small.
But if, well, but we're not.
Well, Vancouver, we're not small.
Yeah.
Kamloops, it's a little bit different. And then Prince
There's-
George being the way that Prince George is, it's a sprawl.
Yes, but it doesn't have to be.
It doesn't have.
And it could have biking infrastructure. We could have a downtown, like, would
Yeah,
be nice to go to.
A densified
Yeah.
downtown.
Yeah, people want that.
Yeah, well,
Not everyone,
not everybody.
but there are people that do want it. And if they had that choice, I think we would have a vibrant town.
We're going back to the 50s where white picket fence, yard, garden, whatever. And that ideal has permeated all the way to this time frame.
Well,
It's from, like, I've known a lot of people in this town who moved up from the bigger cities because they didn't want the cost of living there. So they came to Prince George so they can have more for the same cost or for less cost, right?
but
So-
there's a lot of people leaving the city because they want a vibrant, they want to live in a place with a vibrant downtown.
Yeah.
So there's both.
There's
And, but
both.
there's no choice right now. We have the one, but not the other.
I agree, because I always thought it'd be nice to have more apartment blocks downtown, just revive the whole downtown. You know, that would clear a lot of the problems if you had a lot more people down there, right, as eyeballs and witnesses, so. That, yeah, but it's just, for some reason, every time someone proposed something that was always, it never got built, right? So,
And they want to build just a simple little apartment building. It's been 5 years. They have all the documents, everything in line, and it comes down to money. It really comes down to money. They don't make enough profit off of building or developing, and it's the development side of it.
Okay, well, if we want to stay within the planetary boundaries.
Yeah.
We need to move away from the focus on money.
Yes. Which comes.
But somebody has to pay.
So,
I'll find a move away from money.
yeah, I know,
Somebody has to pay for it.
but
It's
we're-
like, here we can't have mass transit any extent because it's not dense enough and it's expensive to put in the infrastructure.
But
And then ultimately people don't want to pay for it anyway. Like you look at Vancouver, TransLink is, operating at a hell of a loss. But you can ride around on TransLink for next to nothing, like charge people more instead of subsidizing.
I think transit should be free.
So I just wanted to make an interesting, or what I think is an interesting comment with regards to money. I listened to an economist talking about environmental aspects, and he said something that kind of made me think of things in a little bit different manner. He said, the cost of doing something is loosely related to the overall environmental impact. So for example, he talked about the cost of recycling glass, and that if it doesn't make economic sense to recycle glass, it's probably harder on the environment if you're doing it when it doesn't come out the right way from a cost standpoint. Because when something costs, that ends up being money that goes to people that made it, that turn around and use that money as an environmental impact, or it goes to companies that are emitting gases. And so his argument was to remember to consider the cost of doing something loosely with regards to it being a sign of the environmental impact. And so, for example, when we evaluated switching to electric car, we didn't go and buy an electric car and get out of our gas car until it was time that we needed a new car. And so the same thing, I think, with heat pumps. If, for example, you go and spend $14,000 to put in a heat pump when you have a furnace that is only 10 years old, how long before that's a net benefit? And so weighing a little bit on that side of use less, but when you do have to use, make smarter choices. Anyhow, it was just an eye opener to think about that, because sometimes doing the thing that's good for the environment can be very expensive. And I always wonder, do we adequately factor in the environmental impact of that cost?
So the life cycle assessment says, no, we don't, right? And yeah, I fully agree that environmental impact is pretty much proportional to cost. Yep.
Dams made out of concrete, a lot of CO2 there.
But speaking of costs, energy density, I mean, population density, sprawl, super expensive. The utilities, the roads, maintenance, very expensive, tax revenues, relatively small. Especially if you have like the big box stores out in the periphery like we do, it's apparently just terrible for tax revenues for a town compared to a vibrant downtown, which, you know, relatively little maintenance, little infrastructure requirement, high tax revenues. So from a cost perspective, these more dense areas are cheaper per person than the sprawl is. And with respect to cost in general, to changing for the energy transition, we're richer than we've ever been, right? Like our society is insanely wealthy. It's just not distributed nicely. So I think we need to distribute it more evenly and use it to drive an energy transition to one that's more sustainable. Low carbon energy, electrification, efficient passive systems, like efficient houses, walkable, bikeable communities, if you want that choice, at least have it available. But where do you start?
So can you go to your small boxes example?
Yes.
Okay, so that, to the two small box examples.
Yeah.
What do they do to that graph when you said we needed to be at 15? It was like one or two graphs before that slide.
So that would be this
That one there, to the far right.
So that covers that would actually get you fairly close to the thermal comfort, which is, I think, this zone right here, and the transportation, which is here. So you'd be pretty close to a sufficient lifestyle with respect to the transportation and thermal comfort. You still would be, to have this very sufficient lifestyle, you'd need to limit your wardrobe changes. You'd need to, you know, basically share a computer, have only one phone that lasts a long time, kind of thing. So it's a lot more than just moving around and heating your house, but it would get you partway there.
They're made to, right? They're made to not last. It's not like even.
Well, so that's a whole other issue, right?
Yeah, that's, you know, a phone like that.
So
this it has no replaceable battery.
So in a sufficiency society, things are built to last.
Yeah.
Yeah. So that has to be part of this.
Oh, that's okay.
Yes, I think a lot of the problem stems back to our governance structure. We have for hundreds of years had industry government governance that governs for the Hudson Bay Company governs for the early explorers and conquerors who were laying claim to land for Spain to get 10% royalties of all net incomes from the Americas. We still have it today, and we need governments that govern for the people. And that means improving our voting system. Used to be the only people who got to vote in what we call Canada now were those who owned land and were very wealthy and would vote the way that the people running the what we'll call country wanted for decisions, and the voting system was biased to not let others vote. We're getting better, but we got a long ways to go. Then you know, things like recycling. Governments will structure it that you have very limited assortment of materials. So now recycling becomes easier, more cost effective. You don't use the commons as your pollution dumping ground. There's a cost to it. When it increases your healthcare costs, the people making the products pay for that cost.
There's some factories out there, you walk in and 100% of that production will be used once and wasted, right? And that's the mentality that we have to change, where these factories should be, these products should then just be made to be incentivized not to be used for a single use at all, right? So, but there's a lot, that's a big problem as well. But the point is that you can think of a lot of factories you walk into, and everything here is gonna end up in a waste, either burned in a waste heat or waste boiler or thrown in a landfill. So, which is not the way to do it, because there's inefficiencies or are the costs, the efficiency of the cycle around, full cycle around the loop isn't there yet to make it, to close the loop, right? Because you can go, the further north you go, the recycling becomes less and less viable because you have to transport it further and further to get it back to a facility that can process it. So
go down the thing of reusing the whole car, reusing the gas, glass, all the materials and stuff like that. But then they got bought out by Ford. They got bought out by can't remember who's got it now, but it's Indian company, right? They're not in that market anymore. They're not doing that.
yeah, right. You look at some of the things, it's cheaper to get raw new materials than it is to get recycled materials. What sort of logic would that make sense, right? But that's where it is right now. So, you know, it's like you're saying, look, ICE. So it's part of my presentation last week. You can burn gasoline. So for every liter of gasoline you buy, it takes 700 milliliters of it, throw it out the window. You use 30 of it to move from A to B. You go to electric car, then you only use in that 30 units to go from A to B. That's, you know, factor no efficiencies of battery charging that. And then, or, you know, if you take that to the heating system, well, then that liter of milk, I can go 3 times further on that same liter of milk, heating with a heat pump, right? That's, you know, but people don't think that way, right? So.
We also have the problem of the media is on the bandwagon to whatever the highest denominator of opinion is what they're going to go for, because that's where they sell advertising.
Things are changing fast right now, though, one way or another. But yeah, so definitely the farther to the right you go with my green circles here, the more of a values change is required. But I don't think you need to change the entire values of the community to put in a bike lane or have a denser part of a community. And you definitely don't need a change in values to switch to an EV or put in a heat pump. Like you say, when your car end of life, next one should be an EV. When your furnace dies, the next one should be a heat pump.
So we have Jeanette Lorenz online. She's down in Valemont and an EV driver and recently a solar system installer or has solar, not that she installs them. She has one installed. Anyway, she says, thank you very much. Really interesting discussion. I just started to calculate my carbon footprint. I will try to make a comparison for before I had my EV and solar system and after. Not sure she's still an engineer, but she was an engineer, so very capable of doing that. So Jeanette, we would love to have your comparison. Oh, she says retired. Love to have your comparison at some point in the future. Love to see that. And I'm wanted to go back to the recording. This session's been recorded and it's posted to the university's energy transition group webpage if you want. I'm going to go back and look at some of the numbers because I've wondered about the solar systems, how much carbon is involved in the product of making the solars versus, you know, your 30 to 50 years of electrical production and just see how clean it is, because none of it's clean, just some of it's cleaner than others.
You know, if you have better recycling and you can actually utilize that product more, that carbon footprint is going to go way down at that point.
Yeah, that's a good point. And I'd like to say something about this data on this slide. So this is greenhouse gas emissions from making electricity with all these different sources. Solar is right here, PV. It's around 50 grams of CO2 per kilowatt hour. This is from the EcoInvent database. It's the 2024 database. So you'd think it's updated, but like I said, these databases are huge and very involved. And so it's probably about 10-year-old data. And for certain things like solar panels and electric car batteries as well, as they come down in price, right? As they get cheaper, their environmental footprint is shrinking with that decrease in cost because they're getting cheaper because less materials are going into them, less energy to make them. So less environmental footprint. So solar, the newer solar panels, they last longer, they're much lighter, they're more efficient. Depending where they're made, the carbon footprint for the electricity should be around 20 grams or even less of CO2 per kilowatt hour generated. So pretty low.
Does anybody know why insurance companies say that after 20 years, you have to replace your solar panels? Like I put solar panels on, I got it added onto my insurance and everything. And they said, you have to take them off and replace them in 20 years.
The
I
new
don't know if
ones-
it's because they're worried about the roof underneath. They said you can't reinstall them, you have to replace them.
New ones are warranted for 30 years.
Insurance company says you have no insurance if you don't take them off, replace them after 20 years.
Wow.
Well, yeah, that's. Look into California, right, because California's had solar panels for the longest period of time. And I think that's where it comes from. It's from the claims from insurance in the California area.
Yes,
It does, yes. Another question. You mentioned the electricity map where we can see in real time which kind of energy we use in BC, i.e. hydro or imported coal or so. I'd be interested in the website address, please.
Electricity
You
maps.
had that at the bottom of the slide. You can go to that slide, then we can
Yeah.
just read that off. And again, you can go to the recording and pull it out from the presentation.
It's also just called electricity maps. I try them. Yeah, just
And there is coffee brewed and there's some mugs here if anybody wants to have some coffee. And I brought an espresso machine. I can make a little espresso if anybody wants a hit and stay up all night. We did a movie night in the parking lot run by an electric truck. And we had coffee and espresso and hot chocolate and stuff there. So we got leftover stuff that we're now going to benefit from at these meetings.
Thank you very much. Enjoy the coffee.
Oh, thank you.
Hi.
Can you
My
bring
other
up
glasses.
the image, the people's
Yes.
videos? She's not showing up on the screen, but she's on here now. If you change
Okay, but that's okay. That's okay. I just sign off. Bye.
Okay. Thank you for joining.
Bye, Doug.
Yeah. And maybe shall we stop the recording and we can just go a little more informal and we'll say goodbye to those online. Thank you, Alan, for joining. On there, it's electricitymaps.com. I'm not sure if Jeanette left before that got up there, but. Okay. Okay.